Again, my name is Tony Spagnolo. I run sales here at Rescale. So a little bit about Rescale. We were founded in 2011. Our global headquarters is in San Francisco. We have an office in Tokyo and soon to have an office in Europe. Our solution is a full stack turnkey HPC platform that can be either used as a platform directly for users who want to run simulation, or it can be used through our API, which is what Aerobics utilized. So our customers range from automotive, aerospace, oil and gas, and also folks like Aerobics who want a platform to be able to easily access HPC, in this case through their interface, which they'll talk about later. We have a who's list of investors. We recently got funded with a Series A round, which was led by TransLink. So our objective in life is to focus on the HPC challenges. Typically, what we talk to clients about is the fact that they have unmet demand in HPC. We can easily fill that demand through an on-demand service, and also being able to access those resources globally. Just before I was on this call, I was on a conference call with somebody from India and Europe, and their challenge is being able to access those resources around the globe. And obviously, total cost of ownership of internal HPCs is higher than everyone expects, and certainly being able to go pay-as-you-go with a cloud service certainly makes life much easier. So ultimately, the benefits that we want to deliver is a turnkey system that can help you innovate your products faster, reduce your overall IT CapEx, and increase your agility to be able to provide the solutions that you want. As I said, Rescale is a turnkey HPC platform that includes a SaaS layer, an application library of over 120 different software packages, the Rescale platform itself, which can either be accessed through the web service, through ScaleX, or through the API, and the API is what Aerobics will talk about today. And obviously what we then bring to bear is a very secure set of global infrastructure that can be accessed directly from your desktop. For the ScaleX process, it's very easy. You can go to rescale.com, sign up, select the software. We need to do license validation, that you're licensed for that software, and then ultimately be able to select the hardware that you need in the quantity. We have a worldwide set of infrastructure in Europe, Asia, Latin America, North America. This provides you a robust matrix of hardware ranging from GPUs, CPUs, InfiniBand, Intel Phi. So whatever hardware combination you need, we can provide somewhere in the world. Each geography has a different combination, but generally we offer the most popular hardware combinations in the various geographies. So regardless of where your users are, we can offer those. We can offer that hardware. We certainly have a number of infrastructure partners, including AWS, Azure, and SoftLayer. Now, certainly one of the first things that comes up anytime we talk about the cloud is security, and we've built a very robust set of infrastructure that's secure. In particular, what we do for every file that you provide us, it can be encrypted at your site, sent to us through a secure channel, and it remains encrypted on our site except when it's during execution. During execution, we put additional security layers on the cluster, and anytime a simulation is complete, all the results files are encrypted before they go to long-term storage. In fact, we can't even read your files. If you want support from our technical staff, you have to share that model with us so that we can read it. So we certainly can go through this in more detail if you require, but security is number one for us. Just a small case study. So it's very common in the space industry when they build a model of a certain system or subsystem, that they perturbate that through a statistical variation, sometimes Monte Carlo, sometimes design of experiments. So the challenge with that is they need to run thousands of simulations around a nominal model. Doing that on an in-house cluster could take up to a month. So with our space customers, we've been able to reduce that time down dramatically using the cloud, being able to deliver those results in days versus weeks. So again, my name is Tony Spagnolo. If you have any questions around Rescale, you can email me at tony@rescale.com. So what I'd like to do now is introduce our speakers from Aerobics. As I said, Aerobics expertise is in providing patient-specific computational hemodynamics. They've developed what's called the vascular modeling toolkit. They've interfaced that to Rescale using our API. Our presenters today are Luca and Simone. Luca being the founder and CEO, and Simone being the technical expert on the IT side. So with that, I will get out of my presentation. I will hand this over to the Aerobics team, and they will present on their exciting technology. So, okay, you guys are now the presenters. Feel free to go ahead and start. Thank you.
Okay, thank you, Tony. Thank you to all the attendees for being here with us. We're making a short presentation on what the VMTK Lab and the partnership with Rescale is about, and then we're going to give a brief demo in which we illustrate what the system does and how you can leverage Rescale infrastructure. We are a small company in northern Italy. We are certified to develop software as medical devices, and we are into the life science, manufacturing, and energy environment fields in which we develop algorithms and end-to-end systems to achieve solving hard problems. What is computational hemodynamics, which is what we're presenting now with our VMTK Lab software, is, in a nutshell, is about simulating blood flow patterns as they happen in a human body, and simulating how the flow patterns might be, starting from medical imaging data. Here we see on the left 3D rotational angiography data set, from which you can extract a 3D model and generate a mesh out of the model. And in this case, it's a vessel in the brain. It's an internal carotid artery with an aneurysm, which is a pathology. It's a ballooning of the vessel, which tend to rupture over time. So, and this is a catastrophic event. So in this particular case, a clinician or a clinical researcher might be interested in learning more about how the blood flow interacts with this pathological formation, and how the, for example, jet that enters the aneurysm impinges on the wall, and what is the level of shear on the wall. And so being able to do that on a patient-specific basis opens up a few possibilities for a clinician to have a better understanding of the therapeutic strategies that might be established for a particular patient. In the end, we're talking about a quantitative approach to something that many times sits in the head of an experienced clinician from a qualitative standpoint. And this has implications for atherosclerotic plaque instability, coronary artery disease, rupture of intracranial aneurysms, and abdominal aortic aneurysms, among other diseases of the major blood vessels. And why this is important is because there is a relation that has been demonstrated in the last 20 years between the force exerted by the blood on the inner lining of cells on the vessel walls, and how these cells behave. If the flow is laminar, unidirectional, then cells do not exhibit, for example, an atherosclerotic-prone behavior. And in areas of disturbed flow, on the contrary, they, for example, increase their permeability, they lose their orientation, and they become more prone to developing an atherosclerotic plaque. And similar mechanisms are hypothesized to happen at the level of aneurysms, as we've seen in the previous slide. So this interplay between the blood flow and the vessel wall leads to the interest, has led to the interest in the last 20 years to studying what the washer stress in a patient might be, and how this might influence the progression of the disease or a therapeutic decision on the patient. Up until now, this has been primarily a research question. Very recently, about 1.5 years ago, the FDA approved the first use of a patient-specific simulation as a medical device, as an non-invasive device to help evaluate fractional flow research, which is a biomarker. It's a parameter that helps determining if coronary artery, coronaries are the vessels that feed the walls of the heart, if of the section of these arteries is relevant or not, and it should be treated or not. And this was a major milestone for the use of simulations in clinical decision making. This was the first experience led by a group in Stanford, HeartFlow. And the VMTK Lab is not a medical device. It is targeted towards clinical researchers, and the focus is to make it easier for clinical researchers to build up evidence on larger scale studies that can then lead to the approval of hemodynamic related biomarker as a device or as an approved biomarker for clinical decision making. So it's all about, the VMTK Lab is all about making it quicker to build models and run them and extract quantitative parameters out of them, targeted towards clinical researchers and not necessarily highly technical people. And this is essentially what the VMTK Lab is. So it's unlocking computational hemodynamics towards clinical researchers. And we do that in two ways. One is to offer easy-to-use workflows to go from images to computational meshes to simulations and to post-processing. And then, thanks to the partnership with Rescale, to give the possibility of running simulations on cloud computing resources. So it doesn't require you to have in-house HPC or powerful workstations, but it allows you to scale up your simulations in, for example, in a clinical study, depending on your needs. The VMTK Lab can be purchased on the vmtklab.aerobics.com website. And you can also request a 7-day trial to see if it fits you. So what is a typical computational hemodynamics workflow? You start from images, top left. You go on to building a surface model, which is one of the steps that, of course, will determine your geometry. So will have a strong impact on your hemodynamics. So hopefully you want to do a good job here and to use tools that give you full control on what you're doing and track what you've done in a reproducible way. Then you can, thanks to the algorithms contained in VMTK Lab, you can analyze geometry, for example, by extracting the center lines and having quantities like torsion, curvature, and so on, radius along the vessel, which might help you establish correlation between the geometry of a vessel, how it looks like, and what the flow patterns are. And to build a mesh, and possibly a mesh that scales with a local radius, so you're optimizing your mesh size by knowing where the flow will be more or less challenging to simulate, and then to visualize and post-process results. And this is what VMTK Lab looks like when you first access it. It's made up of a few workflows, and we're continuously developing new workflows. You have a workflow for segmentation, and which is extracting a model from a medical imaging data set. Then you save data from that workflow. You can load it up in another workflow. It may be to compute center lines, to process the surface in order to obtain a CFD-ready model, to do mesh generation, and to access Rescale infrastructure through VMTK Lab to run CFD on the cloud by Rescale. So in this case, you will not necessarily access, or you will not access Rescale's website to run simulations, but we are using Rescale's APIs to interact with the Rescale resources and send and submit simulations over to them, and to get results, and results are post-processed in the VMTK Lab. The solver, so the VMTK Lab ideally supports several solvers. What we have released right now is support for a solver that we have developed in collaboration, well, Lorenzo Botti from the University of Bergamo has developed, and in collaboration with us. It's called Multidigetto. It's an incompressible Navier-Stokes discontinuous Galerkin solver. It supports a geometric multigrid with agglomeration of elements, and it has the peculiarity of being fully coupled. So it's not a split scheme solver, but it's fully coupled. It's monolithic, so it solves all unknowns at the same time in a fully implicit manner. It's at least second order in space and time, and you can increase the polynomial order to increase the accuracy of the simulation without necessarily remeshing. It supports arbitrary structures grids with multiple elements, and it's been optimized for pulsatile regimes with fast transients because it has a adaptive time step. So it will refine the time step where you have fast transients and relax it when you're when the flow is changing less. And it's scalable. It's based on PET-C and MPI, so it scales up well to several cores. You can get more details on the solver on the vmtklab.aerobics.com/CFD page. So I briefly mentioned it. You have your user on the right. The user uses VMTK Lab, which is an installed application installed on your computer. You create a mesh. You set up the simulation parameter. You make sure you have enough credits on your account, and you submit the simulation, as you will see in a minute. And the mesh is transferred to our servers, and from there over to Rescale. Our servers only mediate the traffic with Rescale and submit the simulation and take care of then downloading the data over to VMTK Lab. So we're ready for a demo. Yeah, I see that Tony rightfully said, feel free to provide questions. In particular, provide questions on what we have just been said, we have just said, and we'll move over to a demo. Simone will do the demo, and I'll do the talking. So this is the VMTK Lab. So you see the modules as you can. I'll briefly mention it. You can ask for specific workflows. So we do typically as Aerobics verticalization of VMTK Lab with modules that can be proprietary. So based on this technology, we already have a few experiences verticalizing VMTK Lab and for particular applications. What we'll show you right now is a brief overview of what a typical workflow might be. So we're starting from the segmentation module, which is used to load an image. You can load DICOM images or images in other formats like Nifty, Meta Image, NERD. And this is the way you see the medical imaging data set. And here you see in the middle of the image, you see a large aneurysm. This is a 3D rotational angiography data set of a head. So you only see the vessels because this is the way the imaging modality works. It works by injecting contrast agent in the vessels through a catheter through the femoral artery up to the that's inserted through the femoral artery up to the carotid artery. Then the contrast is injected, and two acquisitions are acquired, one before the contrast, one after the contrast, and while a C-arm of the X-ray system is rotated, the two images are subtracted, and this is the reason why you only see the vessels coming out of the image. So if you need to do a segmentation, you want to initialize the segmentation. We offer several techniques to do that. They have been documented in the literature, but essentially the first offers you the possibility to individually segment one vessel you're interested in. Typically, if you want to do a simulation of a blood vessel or a set of blood vessels, you want to control which vessels you model, because there are a lot of vessels, of course, in the brain, but you're only interested in what's upstream your aneurysm in this case, and somewhat downstream. You're not going to pay for a full-blown simulation typically. So colliding fronts is a technique that allows you to do that, to focus on a few vessels. We can proceed, for example, to instead visualize a full vascular tree. You can find details on the initialization method on the website. And this is roughly what the vascular tree in this data set looks like. And once you accept the initialization, you can go on to a phase where the location of the surface on the image is optimized according to some criteria. And the typical criterion is to snap the surface in the location where the contrast agent signal changes the most between inside and the outside of the vessel. So you have a reproducible way of determining what the theoretical location of the vessel wall is. And in fact, you have no information to do better than this. And so you have to wait a little bit until the deformable model. It's a deformable model, so it's actually a partial differential equation describing a deformable surface that evolves under a few terms. One of them is the snapping of the surface to the location of maximum change. So this is the model. You can export. You can segment other branches from here. For example, if you saw that there's one branch missing, you can add it selectively, or you can just export the data and go on with the work. You typically you can export the segmentation itself, the level set, which is the deformable model, or the STL surface if you want to export it to an external software. We're quitting the workflow because we're going to show you how you compute center lines. So by entering, you can start, for example, from an exported STL model. You can avoid smoothing in this case because the surface is already quite smooth. You can place one source seed and one target seed, and you can compute center lines with an algorithm that has been published by our group a few years ago. And it's based on solving a partial differential equation on the Voronoi diagram, which is that medial axis type thing inside the vessel that you can see there. And you can, from that, you can infer what the radius is and other quantities like curvature and so on. And you can export the center lines to use it for analysis, for example, in MATLAB and so on. On to pre-processing. So typically, once you segment a surface, you want to change it a little bit to prepare it for a CFD simulation. And what you do is, for example, you can clip a vessel to open it up, or to just clip a vessel that is. Sometimes you get very tiny vessels that you don't want to model because you don't know the boundary conditions for those vessels, and their hemodynamics doesn't matter that much, so you don't want to pay for that cost. And so you can clip them away and then cap the hole that's left. In this case, we will clip the end caps of the model because the segmentation produces a closed surface, so we have to open it. So now Simone will do that. You have to place a seed to identify what is the portion of the model you are interested in, and then you can place a seed to specify where you want the model to be clipped. And this is the way you do it. It's very fast and convenient. So we can proceed. Here we can cap eventual holes that we produce by clipping. For example, if we wanted to clip the small vessel I was mentioning before, there's a hole left in the surface, and you can cap it. In this case, we don't want to cap the endpoints, but rather we want to probably add cylindrical extensions to the surface so that the boundary conditions do not influence too much your solution, and the solver behaves better. Okay. To do that, we have to import center lines, and we can generate the extension. Okay, and this is done automatically. And once we've done that, we can accept and continue to the next step, which is remeshing. You can remesh the surface to improve the surface, the quality of the elements of the surface. This is useful if you want, for example, to generate a mesh with an external mesher. So you provide the external meshing software with a good mesh. In this case, we won't do it because we are going to remesh the surface anyway in the mesh generation module. So going to the mesh generation modules, yeah, we are notified that for meshing to work, the surface has to have the open end caps in the inlet and the outlet. It has to be open, otherwise the procedure will not work properly. So it was just a reminder. Okay, so this is the model that we chose to mesh. You can have a radius adapted mesh, which means you import the center line, and you can make the density of the surface adapt to the radius. So you're going to have roughly the same number of elements across the cross section, even if the vessel becomes small. And this is convenient when you want to simulate flow because, of course, flow tends to scale with the size of the vessel. And you can choose the level of refinement. You can do a fine or coarse mesh, and you can add boundary layers to the mesh, which are prismatic boundary layers with a triangular base. You can make multiple layers and have a different ratio between the elements in the layer and the total thickness of the layer. Okay. And we are going to visualize the mesh in the CFD module. So we're going to enter the CFD on the cloud module with the mesh that we generated. We're avoiding generating the mesh because it takes a minute or so, so we want to just proceed. Here we have the two options. Go to the control dashboard, which is the dashboard you use to interact with Rescale, or launch a new simulation or prepare it anyway. So we enter, we load the mesh file that we generated in the previous step. We're loading up decently fine mesh. Remember that with multi-digetta you can increase the number, the polynomial order of your simulation. So you don't necessarily need millions of elements. You need enough elements to represent your geometry correctly, and then you can increase the polynomial order. In this case, we have 600,000 elements in this mesh. The first thing we have to do is to provide a unit of measurement of the of the space in which the model lives. In this case, the model has been created using a medical imaging data set, which is typically in millimeters. And the system shows the vessel radius, so we have kind of an idea what the radius for the inlet is. So it cannot be centimeters or meters, it must be millimeters. It's just a help. We can choose the solver. As you can see, we already mentioned that we'll also have the possibility in the future to run Fluent and OpenFOAM. Right now, it's just our own solver. And here we have to specify at least one inlet and one outlet boundary condition. You see the red arrow. We have to decide if each boundary is an inflow or an outflow. In this case, the lowermost is an inflow. We specify a flow rate. We can specify the waveform. Now, we included a waveform by default. We may change it in the future or add more, but the most important thing is that you can generate your own through a file, and you can specify a waveform from the file and will be imported. And the outflow is just zero pressure outlet boundary condition. We specify the heart rate, viscosity, density, how many cycles we want to, cardiac cycles we want to simulate, and how many time steps per cycle. Remember here that the solver is fully implicit, and it will increase the density of the time steps if they are fast transient. So this is just an indicative figure to set the time steps. It's just an order of magnitude estimate of how many time steps you will find in the solution. I mean, once you've done this, you can go to the hardware configuration, which is a place where you select the kind of instance that you will run on Rescale. And of course, the more cores you select, the more computational power you have on Rescale. Of course, the more you will pay for that. But it's interesting because you can, with just a slider, you can go from a workstation level simulation to an HPC level simulation if you have to run fast. You can also check the low priority option, which is an option offered by Rescale, by which you're not guaranteed that your simulation will start right away, but it typically it starts in a reasonable time, but it runs at half the cost. And you can also run a preview test mode. So with the same mesh, using a zero polynomial order, so as fast as a simulation as you can run a one cycle simulation to kind of have an idea if you made any mistake and how the solution might look like from a mile away. And for this, you're not going to pay the fee for the solver. So you're just going to pay the fee for the time you're actually running. It's a preview test mode for which you just pay the computational resources. Then you set job name, and you can create the CFD job. Right now, we are not doing it simply because it will upload the model to Rescale, and we don't want to waste our bandwidth for the webinar. So we quit, and instead we prepared a list of simulations on the dashboard, or one simulation on the dashboard. Okay, this is what the dashboard looks like. On the top row over here, you see your credit, your available credit. You have a refresh button and a quit button. So the way it works is that you pay for your credit, you fill up your credit, and then you use it. Of course, you have an estimate of how much the simulation costs per hour. So you can figure out if your credit is enough. You can, of course, recharge your credit while the simulation is running, and you will be notified if you're going to run out of credit in a few hours. So the information panel is, you have an ID, which is assigned automatically. It's a unique ID. You have a name that you assigned at the previous step, when it started and when eventually it's ended, how many hours it lasted, the cost per hour, the max runnable time according to your credit, and the status. In this case, it's ready to be launched, and the actions and information, if there are any, and the action. And the action means that you can launch, stop, or monitor the simulation, so visualize the logs, essentially, or download the results. You can find a manual on the website. And this is the way you interact with the Rescale. So it's really easy. You're able to increase your credit by logging in on to the vmtk.orobix.com website, the same place where you purchase VMTK Lab licenses. Once you run your simulation for an hour, a few hours, depending on your model, you can download the simulation results with the button that we just saw in the previous screen, the action button in the dashboard, and you can import it in the post-processing module. Here, to import a CFD solution, at the moment you have to specify what the solver was, the viscosity, and how many cardiac cycles, and how long the cardiac cycle lasts. This will be automated in a future release. Right now you have to remember it. You can enable the computation of, for example, a lambda 2, which is a surface that visualizes vortex scores. It's useful if you're interested in vortex scores. It requires a fairly refined simulation to show properly. And you can enable the computation of time average or shear stress quantities like the oscillatory shear index and so on, which are quite used in the computational hemodynamics community. The resolution there is just the standard resolution, is that you can load up low-res version in terms of time steps. So of the simulation, so you can load all the time steps or a subset of the time steps for when you want to make smoother animation. Okay, so right now we'll load a workflow that we saved, a post-processing workflow that we saved. See? One thing I didn't mention while this is loading is that at any time you can save the state of a workflow and then you can reload it back. You can in the VMTK Lab for all modules. And one convenient thing is that you can store a workflow and passing it to a colleague and open the workflow. And the colleague will see all the steps you've done and the state at which you left it. So it's good for collaboration. So this is what the CFD solution module, or post-processing model, looks like. You have the waveform on the left, and you can visualize the surface in colors, and you have a color bar that you can change, and you can change the number of colors you do in most engineering programs. And at the bottom, you can set a customized range for the quantities that are visualized in the legend. You can rescale to the data range of that particular time step or the data range of the whole cycle. And you can toggle the legend, so it's very simple. We can animate the in time, and the animate is pretty much real time. And you can see with a green dot where in the waveform you are with respect to the rendering screen, and you can also go back and forth manually. Other quantities are, for example, work shear stress. Again, we have the work shear stress in time that we can show. The work shear stress is the shear force exerted by the blood on the wall, which is what the endothelial cells are supposed to feel. And this has been demonstrated in experimental work since the 80s. And this is the wall shear stress in vector mode. We will increase the number of post-processing options in the future, of course, by allowing you to select regions, do averages, and so on, and to export the data in tabular format. So this is the oscillatory shear index, another index. And we can also show the other, for example, speed isosurface, which is good if you want to visualize where the jet coming in the aneurysm is going to impinge. In this case, it looks like there's one jet, and you can change the level of the isosurface with control on the right. And the last thing we're showing is the particle path lines. You can animate the path lines in real time, so you can create, and this is a real-time simulation, so you can spin the model around and try to make sense of what the flow in the aneurysm is. Okay, so we're done with our demo of VMTK Lab and how you interact with Rescale resources. We're just showing one last slide about the pricing. With the module, which is €24, you get €10 of free CFD credit. And the price per hour is €15. If you have needs for large-scale studies or educational, we can change the rates to a flat rate, and you can call us for that. And we get a promotional price for all the VMTK Lab modules at €69, and you can contact us for a 7-day trial. And that's it for us. Thank you very much.
Thank you, Simona. As I said to everyone, if you have questions, feel free to ask questions either through chat or questions. And so with that in mind, I do have a few questions. The first one is, how does VMTK Lab help you to define the parameter values?
So there are a few settings. Well, we tried to use settings that were reasonable for reasonable use cases. There are some indications on the website, and if you have suggestions or needs on how to increase the user friendliness of setting the parameter values, feel free to signal that to us. I would say that the best way to go with the software is just play with it a little bit using the guidelines that are on the website and see the effect that the various parameters have on the model. It's quite intuitive. You just have to give it a bit of time to experiment and see what comes out of it. And we are, of course, available for any clarification.
Thanks. So next question is, what's the boundary conditions on the heart flow?
The boundary condition is blood flow rate, and the waveform is scaled with the blood flow rate. So you can say, I have a certain waveform in input, and which shows the blood flow in time, which is normalized, and then you specify what is the total blood flow with a text box, and this will translate in a Wormersley velocity profile at the inlet, which is also why we need flow extensions. In the future, we are working at more advanced boundary conditions, but this is what we offer for now. And for the outflow, we have zero traction boundary condition.
Great, thanks. So next question is, have you done any tests to determine what the speed up and the scalability is across number of cores?
Yeah, so I'll give it to Lorenzo Botti. 1 second. The question is about the scalability with the number of cores of the solver.
So hi everybody. The solver is supposed to scale pretty well up to 100 core and even more. So it uses PET-C and MPI, so pretty validated open source software.
Yeah, I want to mention that there is publication mentioned on the website in which you can find the details of the on the convergence properties of the method and the scalability of the solver.
Great. So I've been flooded with questions. They're all very good. We'll try to get through as many as we can.
Good.
Can you run user-defined functions during the flow simulation?
Not right now, no. And I think we want to keep the current solver, the solver that you want to use when you want to do a large-scale study, let's say, because it's stable, you can, and it's accurate, and it only does incompressible Navier-Stokes, Newtonian, and rigid walls. We will be increasing our offering in terms of solver by including, for example, ANSYS, Fluent, and OpenFOAM to give more flexibility in more advanced cases. But that's our idea for now. Of course, we can change it in the future, but that's the plan for now.
Great. Can VMTK Lab be used to predict occlusion in aortic stent grafts considering different configuration and anatomies?
Okay, so occlusion depends on the end goal for the occlusion. For sure, you can make a model if you make a CT scan, for example, of a patient with a stent graft. You can build a model, and you can predict what the velocities in the aneurysms are, and the shear and the pressure fields, but you cannot predict a phase change or coagulation. So that you can't do. So if you're stopping at the level of looking at the flow, then yes, but then you have to take the leap to hypothesize what, for example, slow flow inside the aneurysm might imply for the occlusion. But right now we don't have any advanced multiphysics model that can simulate, for example, formation of a thrombus. It's possible that in the future we'll add support for multiphysics solvers.
Great.
Rescale will enable that, so we'll think about it.
Thank you. I think this question we'll kind of have to take together. What is the maximum number of cores that can be used? So I guess I'm not familiar with this. Have you guys done any limitations on your user interface to cap the number of cores?
Yeah, there is a, let me just ask Simone, what is the maximum number of cores that we are setting? 100 right now in the user interface, but that can be changed very easily. It's up to you, I think, Tony.
Yeah, for us, depending on what core type you're selecting, I mean, you're fairly safe selecting thousands, if not 10,000 cores, but we would need to get into the specifics. But it's a good question, and I think for most people, there's not a practical limit to the number of cores that you could access via Rescale.
The simulations are typically not very large in terms of number of elements, so at some point there's a trade-off that you meet, but for sure, being able to scale at will, it's a big plus of our partnership.
Yeah, I think traditional rules of thumb are 50 to 100,000 cells per core, and then you start to get degradation. But that depends on the solver and a number of other parameters. And so I'm not sure what your cell count is, but that's sort of a rule of thumb out there. Next question, can you talk a little bit about storage costs? Do you charge for storage?
No, we don't. Typically, you want to download your results, but you can keep them there for some time, a few days, and then you download them locally. So we don't provide storage as part of the offering in VMTK Lab. Of course, we can provide storage in terms of one-to-one relationships that are established with us in case of need.
Yeah, I'll try to get through the rest of these questions. I think we have about 20 in total, but I'll try to select a few more. Related to inlet conditions, is it possible to impose a parabolic profile or just a flat profile?
No, it's not a flat profile. It's a Wormersley profile. So it's like parabolic, but in time. So when you have a fully developed flow in a cylinder, then you get a profile which is not parabolic if the flow curve is not constant. If it's periodic, you get a profile that changes over time, and it's not a parabolic, but it's Wormersley. And this is what we impose. So it should be fairly the right thing to do for Dirichlet boundary conditions at a cylindrical inlet.
Okay, last question. Do you use cloud all the time for solutions, or can you use your local computer as well?
Well, for your local computer, you can, of course, export the mesh and run your favorite solver. We will provide exporting the mesh in different formats. So you can certainly use your own solver. Right now, we're not providing our solver, the one that is on the cloud. We might want to do it in the future. We haven't considered this possibility.
All right, so that's the last question I'll take. We're coming to the top of the hour. I certainly appreciate everyone's attention. I appreciate the team from Aerobics. I've never seen so many great questions in a webinar. I think we have about 20. And so we didn't get through them all. I'll provide the Aerobics team the questions, and hopefully they can answer them directly. As I said, this was, yes, no problem. This was recorded. It'll be on rescale.com. And are you going to put it on the Aerobics website as well?
Sure. Yes.
Yeah.
For sure.
Okay. Anyways, appreciate everyone's time. This is the conclusion of our webinar. Appreciate the Aerobics team joining for this fantastic webinar. Everyone have a great day, evening, or morning, depending on where you're located. Thank you.
Thank you all. Thank you for attending from me and the Aerobics team.
Thank you. Bye-bye.